JFET and op-amp. And then the next type of oscillator is called Wien bridge. We will also look at tuned oscillator circuits today, I believe, and a little bit of discussion on crystal oscillators if we have time. So about your second quiz, quiz 2, I intend to have the second quiz on March 1st, which is 2 weeks from now, because March 8th is probably your last class of the semester, or March 10th. So we should do a week before the final week. That is Tuesday, March 1st. That is my intention to give you the second quiz. For the second quiz, the topic is from after the midterm. But for the final exam, everything is included. So for the final exam, you have to study the whole course topics. This is a Wien bridge oscillator. It looks like a bridge circuit. For those of you, I think all of you have studied the basic circuit theory and also the circuit lab. We do an experiment using a bridge circuit. 4 resistors are connected in a bridge configuration, and then there is one unknown resistor which you have to find. That one is called the Wheatstone bridge. This one is a practical oscillator circuit using 4 resistors and 2 capacitors. This is also known as an RC bridge circuit. So it's using an op-amp and RC bridge. The oscillator frequency is set by the R and C components. But which of them? You see there are 4 resistors, R1, R2, R3, and R4. The resistors R1 and R2 and their associated capacitors C1 and C2. They are the frequency adjustment elements. R3 and R4 are not calculated in frequency adjustment. As you can see, R3 and R4, they are not connected with the capacitor. Only R1 and R2. With R1, you have a capacitor in series. In this example, R2, you have a capacitor connected in parallel. The oscillation frequency is given by this formula, 1 over 2 pi and then square root of R1 C1 R2 C2. There is no R3 R4 in the calculation. So what is the function, or what is the purpose of having R3 and R4? R3 and R4 are responsible for providing the feedback. R1, R2 with C1 and C2 are responsible for providing the frequency adjustment. The bridge inputs are at here, point A and point C in the circuit. The bridge output is at point B and point D. As you can see, point B, point D. So this combination of resistor and capacitor, a portion of the output comes here, point A, with respect to your ground. That's why point A and C are called the bridge inputs. Whatever you get out of the bridge, coming out of point D and point B, going back into the op-amp. When we have amplifier, we have to think about input impedance and output impedance, and also something called the loading effect. The loading from one side to the other side. If you have multi-stage amplifier, you have to think about the loading of subsequent stages. On the input side, if you have something connected, you also have to see the loading effect. But if you neglect the loading effect, there's an analysis of the circuit, of the bridge circuit. It's like this. In this circuit, if you think about the impedance, R3 divided by R4 it will equal to R1 over R2 divided by C2 over C1. Sorry, add C2 over C1. R1 divided by R2 and then C2 over C1. This is the equation. If you neglect, try to ignore the loading effect. This is impedance. The frequency you can also derive. There is no need to do the derivation because it's on the formula sheet. If in this particular example, if you set R1 equals R2, so two resistors are the same, and then if you set C1 equals C2, the equation is further simplified. Let's say R1 equals R2, so we call them R, and C1 equals C2, we call it C. What will become of the equation? What is F out? You have a square root, and then you take R1 equals R2, C1 equals C2. So you have R square and C square in this formula, but you take a square root. If the resistors and capacitors are equal, your output frequency FO will be 1 over 2 pi R times C. When R1 equals R2, so you have 1 and 1. R1 equals R2, they are the same, the ratio is 1. C2 equals C1, the ratio is 1. If that is the case, you have 1 here, you have 1 here. The ratio of R3 to R4 then becomes 2. If you have a ratio of R3 to R4 greater than 2, there will be enough gain in the overall feedback loop or oscillation loop in order for the circuit to oscillate at the given frequency, which is given in the equation 1 over 2 pi RC. Now we are assuming R1 and R2 same, C1 and C2 they're the same. But if they're not the same, then you take the actual values, you don't do that. We can look at an example. This is a worked out example in the textbook. You can open your textbook or you can do from here. It's up to you. This is a Wien bridge oscillator. What is the resonant frequency, the oscillation frequency of this oscillator? We can try to calculate it. As I have said, the R3, R4 resistors are feedback elements. They are not part of this calculation. Is Mr. Borapat here?
Yes, sir.
Okay, so I'm going through rotation of students. Your name is next. Because previous class, the previous person, we finished at the previous person. We can calculate the output frequency, the resonant frequency of this circuit. Can you tell me what formula I can use in this case to calculate the oscillation frequency? It's 1 over 2 pi, and then you have a square root of R1, C1, R2, C2. But look at the values of R1 and R2, C1 and C2. What can we write then? That is question for you, Warapat.
Sorry, give me a moment, please.
Okay.
Maybe R square, C square.
There is a square root. Remember, there's a square root term.
Yes, so we remove that's going to be RC, right?
Yeah, when you remove that, it will be, of course, it is going to be RC. So 1 over 2 pi RC. Now you can calculate, please calculate the output frequency of this oscillator. This is a Wien bridge oscillator. Equals how much?
I got 3,125 hertz.
3,125.
Hertz, yes.
Okay, let me check. I'm doing calculation. 51,000 and 0.001 microfarad. Okay, it's a micro multiplied by pi multiplied by 2. Take the inverse, 3,120 hertz, 0.3120.7 hertz. It's actually 0.68. I just rounded up. The unit is hertz. If you want to express in kilohertz, it is 3.121 kilohertz. So this is simply a matter of plug and play. Plug the values in the equation and then you can find out the answer. Any question about this one? So in this case, when R1 and R2, they are the same, and C1 and C2, when they are the same, the ratio of R3 to R4 is 2. If your ratio is like this or greater than 2, the loop gain is sufficient to keep the oscillation going. In the previous class, I mentioned to you, in order for the oscillation to go on, the overall loop gain should be at some minimum point so that the oscillation can go on. If it's less than 1, the oscillation will die down. If it's more than 1, it can saturate. But more than 1 is not problem. Less than 1 is a problem because eventually you will have no oscillation at all.
Teacher,
Yes?
like to find R, like how did, like you just combine all R and then you put it in there?
The formula is actually this. 1 over 2 pi I hope you can see the drawing, the writing R1 C1 and also you have to write R2 C2. You see what is R1? 51 kilo ohm. R2 is 51 kilo ohm. They are equal. So 51 and 51, you have a square, but you also have a square root. That's why you can say R. I don't combine using any series or parallel. I just set R1 equals R2 equals R. Same for C1 and C2. They are exactly the same value, 0.001 microfarad. So if you take this and this, it becomes a square of the same value, and then you have a square root. So I just take C1 equals C2 equals C. We don't combine series parallel. You are multiplying, you're taking the square because you are multiplying the same value, and then you're taking a square root. So that's why if the resistors and capacitors are equal, this formula, this is the original formula. I think this is on the formula sheet. This one is not. The original formula will be simplified like this. That's how we find out R and C. Is it clear now? So did you understand, Krisanapong?
Yes, teacher.
Okay. You can even have a circuit design problem. If I give you the same problem, let's say design in such a way that the output frequency is 10 kilohertz or 5 kilohertz. What will you do? Maybe you set here at 5K. Just pick any value of R, set so that R1 and R2 the same, so you don't have to do with the square root term. You can pick any arbitrary value of R. Maybe you want to take 25K or 50K or 100K ohm. It's up to you. And then from that, you can find the capacitor value C. If you remember the voltage control oscillator from linear digital circuits, VCO, for a good VCO, there are some design limitations. The resistor has to be within a certain value, and then applied voltage, VC, frequency, all they have to be within a certain value. Here you have a bit of more liberty. We don't have such strict criteria, so you can pick any value of R which is sensible. For example, what you can find in the lab, 100K, 50K, 70K, etc. And then for R3 and R4, you should try to get a ratio which is greater than 2 for the oscillation to take place. In this case, what is the ratio of R3 to R4? 300K over 100K. The ratio is 3. Obviously 3 greater than 2. So for the feedback elements R3 and R4, it is better to maintain that ratio greater than 2. If R1 equals R2, C1 equals C2, it is already 2. Next, we move on to another oscillator circuit called the tuned oscillator circuit. Tuned oscillator circuit, the setup is a parallel LC resonant circuit, also known as LC tank or tuned circuit. There are two types of tuned oscillators. The first one, the two types are common. You can have some specialized as well. The common types are Colpitts. In a Colpitt oscillator, you have 2 capacitor, 1 inductor. The second one is called Hartley. In a Hartley LC tank circuit, you have 1 capacitor only, and then you can have either 2 inductor separate, or you can have 1 inductor with a tap connection. You know what happens? For example, you have seen the center tap transformer. By tapping, you can create 2 separate parts. On the right hand side is not showing the actual component. They're showing the building block. So this is your amplifier, and then this portion is a combination of, it has to be a parallel. So you have 2 parallel branches. This parallel branch, 2 parallel branch, they have capacitor and inductor. This part we call the LC tank or tuned circuit. If you remember, I taught you power amplifier, which was the first topic after the midterm. There is one amplifier called Class C power amplifier. The conduction of Class C is actually, the output conduction cycle is less than 180 degrees of the input. However, if you pair a Class C power amplifier with an LC tank and make the Class C amplifier frequency same as the resonant frequency of the LC tank, in that case you will have a 360-degree full cycle output. That's the only way you can have a Class C conduct for the entire cycle. And Class C is used mostly in radio communication circuit. LC tank circuit is also a common application in radio communications. So let's talk about X1, X2, and X3. These are the elements. Let's say we have a Colpitts oscillator. So I'll write the letter C, Colpitts oscillator, 2 capacitor and 1 inductor. So X1 will be a capacitor. Maybe this one is C1. X2 has to be a capacitor. They are in the same branch. You cannot have one capacitor here, one capacitor there, and one inductor. No. In the same branch, you have the same type of element. And then you will have one inductor. This is the Colpitts connection, Colpitts resonance circuit. What if you have a Hartley? For Hartley, I'll write the letter H. You need 1 capacitor and 2 inductors. So where in the LC tank you have single element? This one. This will be a capacitor. This one will be your first inductor. This one is going to be your second inductor. Sometimes what you have is 1 continuous inductor. Let me draw 1 continuous inductor like this. And then you have a center tap connection. When you have a center tap connection, each side of the center tap or the tap connection is considered 1 individual inductor. This is the Hartley. We can see practical examples. The X1, X2, and X3 in the block diagram, we call them the reactance elements, because when you apply a signal means an AC signal which changes direction with time. Resistor does not have any reactance, but the capacitor has reactance. Inductor also has reactance. Formula for capacitive reactance is 2 pi F multiplied by L. Capacitive is 1 over 2 pi Fc. Formula for inductive reactance is 2 pi Fl. The reactance is expressed in ohms unit. Let's look at the Colpitts oscillator circuit. This is not a building block anymore. This is a real example, practical example. So you have an amplifier right here, a JFET. And then this is the radio frequency coil. This one is not the LC tank. This is the radio frequency coil. I told you it's used a lot in the radio communication. Where is your tank? LC tank. Parallel combination of capacitor and resistor. If you look at the bottom of the circuit, this is the tank. This is the tank circuit. You see 2 capacitor, 1 inductor, C1, C2, and then L. What is the combination of capacitor in this circuit? These 2 capacitors in this branch, they are in series. Remember, when you have series resistors R1 and R2, it is just R1 plus R2. But for series capacitor, it is 1 over C equal 1 over C1 plus 1 over C2. Therefore, if you simplify the equation, it becomes like the parallel resistor formula. In this LC tank circuit, since C1 and C2, they're in series, your equivalency you have to calculate as this, C1, C2 over C1 plus C2. And L is just L, just one inductor, you don't have to worry. What is the resonant frequency or frequency of oscillation? 1 over 2 pi square root of LC. In this case, you don't use either C1 or C2. You have to find LC equivalent. This oscillator circuit, Colpitts, is named after a person whose name was Edwin Henry Colpitts, one of the pioneer scientists in radio communications, and this person is American. Any question about the Colpitts oscillator before we go to an example?
I don't have.
So right now, let's try to solve very straightforward the tune oscillators. Given a Colpitts oscillator circuit, sometimes in the exam, it says, given the tune circuit. It doesn't say Colpitts or Hartley. You have to figure it out. The trick to figure it out is to look at the tank area. It's called the tank circuit. If you have more capacitor than inductor, definitely Colpitts. And remember the shortcut Colpitts, the first letter is C, and more capacitor, the first letter is C. This is, I think, example number 9, 14.9 or 15.9. Never mind. Given the Colpitts oscillator, there are two capacitor values given. They are not the same. C1 is 750 picofarad. C2 is 2500 picofarad. L is 40 microhenry. Let me write the formula here. 1 over 2 pi and then take a square root L C. C has to be C equivalent. I'll ask two students to participate in this. Miss Nataya,
Yes.
please find out the equivalent capacitor of the tank circuit. And Miss Pichayapon,
Yes, sir.
please calculate the frequency given this current formula. So equivalent capacitor will be series capacitor formula. You can keep the same unit, picofarad.
577 picofarad.
577. So you round up, okay?
Yes.
That's fine. It's actually 576.9 or something like that. So you can write 577 picofarad.
For the frequency is around 1.05 microhertz.
1.05 megahertz.
Microhertz.
Micro.
Yes.
That is quite unusual. Maybe you forgot to inverse something.
Wait, no, teacher. Teacher.
I get yes.
What is the formula for the equivalent again? Like the capacitor equivalent.
Series capacitor. 1 over C1 plus 1 over C2 equals 1 over C equivalent. So think of the parallel resistor. When you have two parallel resistor, R1, R2, what do you have? R1, R2 divided by R1 plus R2. 577 picofarad is the correct answer. 577 picofarad, and then you have to multiply with 40 microfarad first, 40 microhenry, and then take a square root. Take a square root of your answer, and then what I did is I multiplied by 2 pi, and then I inverse my answer. I have 1.047, 1.05 megahertz, not microhertz actually. So did you forget the square root sign then? Maybe. The capacitor formula is this: C1 C2 over C1 plus C2. In which manner you're gonna get microhertz? Not possible. 1 mega, 1.05 mega. That's what I get. Can you please check your calculation again? See if you can get mega. It's 1.047 or 1.048. I just write 1.05 mega and then hertz.
I got that one. 1.05.
Mega, right? Not micro.
Yeah, it should be mega because it should be mega. Okay.
Microhertz means it's so small oscillation. It really, it's weird. We never have microhertz in any of our calculations. This 577 picofarad about.
Sure, in the calculator, that you calculate, did you get like 1.047 times with the 10 negative 3?
No, I get 1.0477 times 10 power positive 6.
Oh, that's well. Okay.
I think what the students make mistake here, they forget this thing, the square root sign.
I already put for me.
Okay, here, square root. And this is 1 over, so whatever you get, you have to inverse. In order to avoid the mistake, this is what I recommend in the calculator. Take the C equivalent, 577 picofarad, multiply this by 40 microhenry. Whatever the answer you get, take the square root of that first. So this part is done, and then multiply by 2 pi. You will get near the answer. Once you have the multiply by 2 pi value, you see a 1 over. On the scientific calculator, there is always an inverse button. Whatever answer you get, you have to put the inverse, so it will be 1 over that. That is your answer. We can look at another example of a tuned oscillator. This one was done using Colpitts. Hartley oscillator. What is a Hartley oscillator? Just one capacitor, but more inductors. The formula is same format. F, the frequency of oscillation, is 1 over 2 pi and then square root of LC. But there is only one C. You have to find the equivalent L. L equivalent. What is the L equivalent? To find the L equivalent, there is one term we have to include in the calculation. So it's not just, if you look at this tank circuit, two inductors in series, usually L1 plus L2. However, there is something called a coupling factor, because this is a transformer coupling equivalent as well. If you think of this as a transformer, this is the primary side, this is the secondary side. The coupling factor is called M. the values of inductance is given in Henry or millihenry or microhenry, whatever is that. M is also given in the same unit. So if you are given L1 and L2 in Henry, M will also be given in Henry. L1 plus L2 plus 2M is your equivalent inductance. This is, you have to calculate first. This one is a practical example of a tank circuit. Also it's called LC tank. However, this is the Hartley type. It's not Colpitts. Where is the tank? Here. The parallel combination of capacitance and inductor. And the top one is radio frequency coil. We don't use that for calculation. To me, it looks like, how to say, it looks like a voltage divider. You have a BJT, R1, R2, you have RE. Instead of RC, you have a tank. So if you take a class C power amplifier, if we think that this is a class C power amplifier, we make it output with the same frequency as this oscillator frequency, you will have full 360 degrees. We can look at an example of a Hartley oscillator. For this Hartley oscillator, again, will be 2 students. What is it asking to calculate? Calculate the oscillator frequency for this Hartley oscillator. Why does it say FET? I don't see an FET. This is a BJT. It should write BJT oscillator circuit. The given values are for one capacitor 250 picofarad. L1 and L2 each is 1.5 millihenry. The coupling factor M is 0.5 millihenry. Mr. Komchan, present? Is Komchan present? Maybe he went to the toilet. Piradon. Is Piradon here? Piradon, please find out the equivalent inductance L equivalent of the LC tank circuit. The next person in line is Mr. Kritsanapong.
Find what, teacher?
For Kritsanapong, you will find the oscillator frequency. What is the formula for frequency? It's this. I am writing so that you don't have to go back and forth between slides. 1/2 pi and then square root L and C. L is the equivalent L. So I'll wait for your calculation to take place. The first person is finding the equivalent inductance, and for Kritsanapong, you will be calculating the final answer for the oscillator frequency.
One question, sir.
Yes.
Is M always provided?
Yes, M is always provided. Without M, you can't actually solve the problem.
Okay, thank you.
But I may got the answer. I may got the answer for the frequency.
Okay, what's your calculated frequency?
I got 5.03 megahertz.
5.03 megahertz. What value of L you used?
I use 4.
Yeah, 4 millihenry.
Yeah, 4 millihenry.
L1 plus L2 plus 2M. So 1.5 plus 1.5, that's 3, and 2 times 0.5 is 1. 4 millihenry. Capacitance value used, I believe, used 250 picofarad. You
Yes.
said 5 point something megahertz.
5.03 that I got.
Okay, let's see if that's the answer. Take 4 milli, multiply by 250 picofarad. Pico is 10 power negative 12. And then you have to take the square root of your answer. And then I multiplied by 2 pi. I will inverse my answer. I'm actually getting something different. I got 159.15 kilohertz.
One question here. How do you do the inverse? I do not know in my calculator. Have or not?
You can you take 1 over something?
Yes, I can do.
Is there a button for 1 over?
Yeah, the fraction, right? Yes, I have.
If you calculate something and then want to do 1 over that, what do you get?
Moment.
It depends on the calculator, because you are actually allowed certain calculator, and then certain calculator you are not allowed. So I'm showing you my calculator. My calculator, you know, you won't believe it. It's 22 years old. This calculator is 22 years old, but it is still fantastic. It's a Texas Instrument TI-83 Plus, programmable. You can write computer program with this. So my button looks like this.
For
Where
me,
I'm
it's
putting my
like
thumb, it is X1. Sorry, X inverse. Did you see inverse? I'm showing you my calculator. Different calculators have different. So I don't know which model are you using, Casio or Sharp?
one question. You inverse which one?
This one. Look at my thumb.
I see the inverse already. I mean, like you inverse what? 1 over 2 pi?
First, I do just 2 pi LC root over LC. I do that calculation first, and then I inverse so that I get the correct answer. You don't have to inverse it. The formula is 1 over. Or you can just take 1 over already in the calculator.
So you
So
calculate
1
the root
divided,
first.
I calculate the denominator first and then inverse it. Because if you try to put it in the calculator, you have to put so many brackets. 1 over 2 pi, and then, okay, I can multiply. I have to put a bracket. Times square root of, and then you have what, 4 millihenry multiplied by 250 picofarad. Two brackets I have to put. I still get that value.
So you put in like in the formula first, and you click and inverse it, right?
No, if you see the formula is 1 over 2 pi square root of LC. So how you calculate it, it's up to you, as long as it follows the formula. You can try to do with the calculator. The thing is, it might become quite complicated.
I got 198 when I click the inverse.
Anyone else is having this problem?
Me.
I got 159 kilohertz.
Yeah, it is 159 kilohertz.
Yes.
I still confused when I gonna click the inverse one, by the way.
Okay, maybe you don't have to put inverse one. Just calculate exactly as the formula.
Yeah, exact formula I got like 5.03.
Are you missing the square root or
No,
something you're
I
missing?
put the square root in, and then I got like 5.03.
See, how is the mathematic calculated? You have addition, multiplication, dividing, subtraction. If you miss a bracket at some point, you are going to get this kind of funny value. Because I did my first calculation just like you. I missed one bracket. I got microhertz. I got 1.5 microhertz because of missing the bracket. So let me open again for
I still
you my screen.
got the same.
You have to like do it properly. This is my
But
screen.
teacher, but it's weird somehow. Without the square root, I got like 1.59.
See, maybe you can see a bit. It is not too clear for the students. But right now, please look at the video that I opened for you. How many brackets I have to put? If I do directly, so this is in hertz. My answer is in hertz. If you divide this by 1000, you can get 159.15 kilohertz. I think everyone else should get this thing. Phil is sending an image in the general. Yeah, just like that. So you can go to the general post and Phil is just, he has just written the formula. I have also written the formula on the screen.
Teacher,
Yes?
if we calculate like right away using the formula, we don't need to inverse, right?
No, you don't have to inverse. I just
Okay.
showed you a mathematical trick in the calculator. Sometimes when you do 1 over 2 pi, how many brackets I have to put? Let's see. 1, 2, 3. There are
What is your answer again? Huh?
159.15 kilohertz.
Oh, okay. I got it. The same thing now.
Yes. Students miss the brackets, and then the answer that comes out is quite funny. So equivalent L is 3 plus 1,
4.
4 millihenry. 4 millihenry. And then this is 159.2. It's 0.15. I just write it 159.2 kilohertz. 2 small k hertz. I hope the rest of the class you were able to calculate. So only two types of tuned oscillator we study about. Remember, it is called a tuned oscillator. Sometimes it's called LC tank, or sometimes it's simply called a tank circuit. Very common in radio communications application. We have another type of oscillator known as crystal oscillator. It's basically, crystal oscillator is a tuned circuit oscillator using a piezoelectric crystal. So this is a crystal. What is a piezoelectric device? A piezoelectric device, when you apply pressure across one set of surfaces, a voltage, which is a potential difference, it will appear across the opposite surface. Piezoelectric, P-I-E-Z-O. This type of device we call piezoelectric. They produce a proportional or any equivalent voltage which has some relationship to the applied pressure. You just press or add pressure and then it will output the voltage. This crystal is a piezoelectric crystal. This one is working as a tank circuit. In a crystal oscillator, it can actually work as both series and parallel resonance circuit. Usually the crystal is made from a quartz. A quartz is like a material that's found in our planet. It's a natural material. It's like a valuable piece of rock or something. We call it the quartz. Many expensive wristwatches, they use quartz crystal. So in order to provide the oscillation for the watch to continue moving its second hand, they use a quartz crystal to maintain its oscillation. The crystal has greater stability in holding constant the frequency of oscillation at whatever frequency the crystal is originally cut to operate, depending on how you cut the quartz in the factory. Because when you get the quartz from the mine, from the nature, you have to bring it in the factory, you have to cut it, put it in the proper shape, you have to polish it, maybe take away some part. So the frequency of the crystal, the resonant frequency of the crystal actually depends on how you manufacture and cut it. This type of oscillator is used where the circuit requires greater stability, communications, transmissions, and receiving. What is a resonance circuit? You are often seeing this term resonant. The crystal appears like a resonance circuit. It means it's an electric circuit which has very low impedance at a certain frequency. That's the meaning of a resonance circuit. This crystal oscillator, it has two resonant frequencies. The first one is the series resonant frequency. So the equivalent, if you take the equivalent of the crystal and make an equivalent tank circuit, you are seeing the tank equivalent. You see R, L, and C. When the crystal is vibrating at a series resonant frequency, RLC will determine the resonant frequency, and the crystal has a low impedance. If the parallel resonant frequency mode is on, then this capacitor does not do it. So let me draw for the series first. For the series resonant frequency, these three components, they determine the frequency of the oscillation. When it is in parallel resonant frequency, the oscillation frequency is determined by RL and the other capacitor. So how do you know if the crystal will be in series resonance or parallel resonance? You have to excite the crystal. To activate the crystal means to excite it. In order to excite the crystal for operation in series resonant mode, you may connect as a series element in a feedback path. So if you have a crystal in a feedback loop and it is series with respect to the rest of the feedback elements, you can excite the crystal to be in series resonant frequency. At this series resonant frequency, the crystal has impedance value which is the smallest possible, and the amount of positive feedback will be the largest. Let me show you a typical transistor circuit which has a crystal in series resonant frequency. Again, what happens when the crystal is excited in series resonant mode? R, L, and C. This is like inside the crystal. Equivalent. RLC determines the resonant frequency. Now look at the actual circuit. This is a MOSFET. It's a MOSFET symbol. You have radio frequency coil, you have output. A part of the output is being fed back to the input side. So this is the feedback path, and see where is the crystal placed. The crystal is right here. In the feedback loop, it is in series. This is a single loop and it is in series with the coupling capacitor. So if you put the crystal like this in a circuit, it is operating in series resonant mode. It has low impedance. We don't have calculations that I asked from crystal oscillator or even the unijunction. What about a parallel resonant frequency? In a parallel resonant crystal oscillator, these three elements are determining the oscillation resonant frequency. Can you see how the crystal is connected with respect to the rest of the circuit? How is it connected? In parallel. The crystal looks like a parallel load with respect to the rest. If you look back from the output side, these are all parallel nodes. If you connect like this, the crystal will vibrate and output the frequency in a parallel resonant mode. And in this case, the crystal will have high impedance. No example problems to work on, but you should remember the theory for the sake of the exam. What is a crystal oscillator? How many resonant frequencies it has? And in order to do series or parallel resonant mode, how you connect the crystal oscillator and which elements decide. That would be sufficient.
Teacher, can you say the explanation for the crystal oscillator again?
Explanation for the crystal oscillator. Okay, let me go back to the first page of crystal oscillator. So crystal oscillator itself is a tuned oscillator. Here is the crystal. This is the symbol of a crystal. Because it's a tuned oscillator, the equivalent oscillation circuit, the tank circuit equivalent looks like this on the right hand side. On the left hand side, you see the crystal symbol. On the right hand side, you are seeing the equivalent tank circuit. What is a tank circuit? It's a parallel combination of inductor and capacitor. Sometimes you have series branch and then you have another parallel one. It's a quartz. It's a material found in nature. People search for gold, silver, copper, aluminum. So in nature, you can also dig the earth and you can find crystal quartz in many places of the earth. You have to take a quartz and you have to cut and polish it in the factory, just like you cut and polish a diamond. In the nature, you cannot find beautiful diamond. You have some ugly rock, but once you cut and polish in factory, it becomes a diamond, and then you pay a lot of money for it. Crystal is like that. Take a quartz and then cut and polish it. After cutting and polishing, it has its own resonant frequency. It depends on the cut and shape. It's also a piezoelectric crystal, not any type of crystal. A piezoelectric means if you put some pressure across one set of surface, there will be a voltage appearing across the opposite surfaces. In a crystal, it has two frequency modes. The first one is called the series resonant frequency mode. The other one is called the parallel resonant frequency mode. In order for the crystal to behave and operate in series resonant frequency, you have to connect it in series in a feedback loop. So once you connect it in series, the frequency is determined by the RLC. This is an example. You see the equivalent crystals, equivalent tank circuit. When you connect in series in the feedback loop, just like this, R, L, and C will determine the resonant frequency of this circuit. There is another mode of the crystal resonant frequency. We call it the parallel resonant frequency. How do you make the parallel resonant frequency? When you have the crystal behave in parallel mode, R, L, and this capacitor Cm, not the bottom one. These three determine the frequency. So here's one example involving, I believe this is a class C power amplifier, even though it's not written, but since I see a radio frequency coil, this is used in radio communication. So this could be a class C power amplifier. And then that's why you need a tuned circuit. The crystal here is placed in parallel with the rest of the output side. If you put the crystal in parallel, the crystal is now vibrating in parallel resonant frequency. In this case, the crystal will have high impedance. In the first case, when you vibrate in series resonant frequency, the crystal will have low impedance. So that's a recap of the crystal oscillator.
Thank you, teacher.
Welcome. Another one is called the uni-junction oscillator. I don't really ask questions from this. You can skip slide 33, 34, and 35. This is shown using a JFET. The output frequency is given by this formula, 1 over RTCT and natural log of 1 over 1 minus eta. That's the Greek symbol. I think it's called eta. It is called intrinsic standoff ratio. The value is between 0.4 to 0.6. It's a rating of unijunction transistor. What is BJT? Bipolar junction transistor. And then JFET is junction field effect. This is called the unijunction, just one junction. This value depends on the material. If you want a shortcut formula, FO can be approximately 1.5 divided by RTCT. If you take the natural log of, let's say, 1, if I set the eta value to 0.5, 1 minus 0.5 is 0.5, and then that, take the natural logarithm of 2. If I take the natural logarithm of 2, what do you get? 0.7. 1 divided by 0.7 is how much? 1.44. So it's actually like this. The formula, if you take the eta value at half, it becomes 1.44. This resistor RT and CT. You don't have to worry much about the unijunction. This is an example of the waveform. The unijunction oscillator is still an oscillator, so it provides an oscillation. But what type of waveform? This one is called a sawtooth. Triangular is like this. That is triangular. The sawtooth is like this. A slope and then less. Do not confuse triangular with sawtooth. For the triangular is like a symmetric triangle. This one is not symmetric. Also known as a relaxation oscillator. What are some of the applications? If you take the voltage at VB1, there are 2 points, and VB2. They appear as the mirror images. It looks like a pulse, almost like a digital pulse. So if you have a need for pulse input, either a positive pulse or a negative pulse for a digital circuit application, you can use the unijunction or relaxation oscillator. Here's a design problem. Maybe we could try it now, or maybe even in the next class. But you need to know some other term for unijunction oscillator. this is the end of feedback and oscillator chapter. I'll go in the beginning first and then recap some of the concepts, because the feedback is a bit complicated. Let's go to the first page. Actually, this design problem is very simple. Do you know how to solve this? Let's give the formula. F, what is F? You can say that formula 1 over RTCT and then what do you have? The natural log of ln 1 minus 1 over 1 minus Greek symbol eta natural logarithm, so I'll put a square bracket first. Natural logarithm of 1 over 1 minus this is the Greek symbol the value of eta, which is called the standoff ratio, in intrinsic standoff ratio. You can take either any value between 0.4 to 0.6. What value would you like to choose? It's up to you. What value would you like to choose? If I take 0.5, the formula becomes like this: 1.44 over RTCT. So F is given. The first case is 1 kilohertz. You just take the left-hand side of the equation as a 1 kilohertz. Find a value of RT that you like, and then from that you can find the value of the capacitor. Or you can start with a capacitor and then find the value of the resistor. You can do either way. Normally we start with the value of the resistor first. The last slide showing some possible configurations for unijunction oscillator. Case A, you can have RT and CT on top of each other. On the output side, you have R1 on the source terminal. And then the second case, you can have RT and CT as usual, but you have R2 on the drain side. Each case is showing you what type of pulse you are going to get. If you take output from this side, you're going to get a positive pulse. If you take output from this side, from this circuit, you will get a negative pulse. If you configure like this and add another amplifier, what are you going to get? Negative pulse. Why? See, you're taking from this point. The output you're taking from this point, you get a positive pulse, but then you are feeding it with the BJT, which has 180-degree phase shift from input and output. So the positive pulse shifted again by 180 degree, it became a negative one. The last two type of oscillators, crystal and unijunction oscillator, They're more like descriptive topics. You should be able to describe at least the basic fundamentals. Now, if I go back to the top or the beginning of our feedback and oscillator chapter, quickly recap the concept. When we studied first about the amplifier, especially the op-amp, we learned that you can have an open loop gain, or you can close the loop by connecting output with an input. The gain will be less. Usually it's a negative feedback. The reason for providing negative feedback is to compare the output with the desired output. You desire something, you take the output, compare, and if you need some adjustment to keep it maintained, you compare with an input signal. There will be some calculation, and by adjustment you will get the proper output. The benefits of feedback: you will get a higher input impedance, so it reduces the noise. The gain will become less but more stable. You will have increasing bandwidth and improved frequency response. These are some of the benefits. Operation is going to be linear. The drawback means the disadvantages is you have a lower gain. That's the compromise you have to make with feedback connection. We studied about the feedback concept. This is a feedback loop. The total loop gain is given by V out, which is the output signal, over Vs, which is the input signal. It's not V out over V in. If you take V out over V in, that is the gain of, this is gain A of the amplifier stage. It's not gain of the feedback, it's gain of the amplifier itself. This is V in, this is V out, so A is V out over V in. That is obvious. A part of the output voltage is then provided inside the feedback element. V out goes here, Vf goes here, so beta is what? Vf over V out, because V out is the input to beta. This is coming, V out is coming here. V out, let me draw. It is output divided by input, so Vf over V out. So Vf equals beta times V out, and V out equals A times Vi. The overall equation is V out over Vs. When you replace and substitute, finally you have a generic equation which we did in the class. Gain with feedback, we have to distinguish with this letter. A sub f equals A divided by 1 plus beta A. That's the basic equation for deriving everything about feedback. And have a voltage series feedback. In this voltage series feedback using JFET, beta is minus R2 over R1 plus R2. I think this is in the formula sheet already. Open loop gain without feedback is minus GM-RL. So RL you can find from by looking from the output side. RO parallel RD parallel R1 plus R2. The gain with feedback is actually A divided by 1 plus beta A. That is the safe formula to use. But when beta A much greater than 1, you can approximate to 1 over beta. We have seen through examples in the class, if you do it in a wrong manner, you will have more than 25% error. What is the voltage in here? V out R2 divided by R1 plus R2. That is a negative sign, so it's minus V out R2 over R1 plus R2. That's Vf, and then this is Vs. Example 14.3 is just calculating using the given values. This is a voltage series feedback using a JFET. You can also have an op-amp to provide voltage series feedback. For this, you see beta is a positive value, R2 over R1 plus R2. VF is V out times R2 over R1 plus R2. Beta is what? V out over, no, VF over V out. That's beta. So in that case, R2 over R1 plus R2 becomes the beta term. Input is the comparison between the signal and the feedback. Vi is input at the op amp 2 pins. Inverting pin is the main signal. Non-inverting is the main signal. Inverting is coming from feedback. So your Vi equals Vs minus Vf. Here there is no phase shift because you are providing the signal on the plus side. That's why finally you don't have a minus sign. There was an example that we did using voltage series feedback. Frequency distortion Nyquist criteria. We talked about it briefly. You can study the slides 9, 10, 11 as well. We know this when you have feedback, the bandwidth increases. Also 12, when you have feedback, the gain reduces, but the circuit becomes more stable. Also, we have studied that what happens if you have too high of a frequency, the feedback signal may no longer be out of phase with the input. If feedback signal is same phase with the input, they actually keep accumulating. And then you have a positive feedback and then amplifier becomes unstable and may begin to oscillate. However, we can actually exploit this positive feedback and make it an oscillator as long as we can control it. You want a controlled oscillation. Oscillation is not bad if you have a good use for it. 14, 15, and 16 we briefly described, but you can skip it. You can skip slides 14 until 16 for the exam or for the quiz, but 17 you must study. If you want the feedback network, if you want to make an oscillator by using feedback, you need a positive feedback signal. You cannot have a negative. With a negative feedback signal, you cannot have oscillation. You can have some correction. For example, PID controller in the factory. But if you want an oscillation, you need a positive feedback and the gain cannot be less than 1. If the gain is less than 1 for the overall loop, the oscillation will die. Overall gain, if greater than 1, you will reach a maximum saturation point, but it is still better than dampening out oscillation. And we studied different types of oscillator, phase shift. Today we studied Wien bridge, tuned, crystal, and unijunction oscillators. I believe today is the deadline. Today before midnight is the deadline for your homework assignment number 4. So once we have completed another chapter, feedback and oscillator, and the next chapter is called power supplies or voltage regulation. Once we complete power supply and voltage regulation, there will be a final homework number 5, which is a combination of these 2 chapters. Those who came late, again, I would like to tell you your second quiz I intend to take on Tuesday, March 1. So be prepared for that. We have about 2 weeks from now. For the second quiz, the topic is only from after the midterm. But for final, I would like to remind you that everything from the beginning of this semester until the end is included. That's for the final. Are there any questions from this chapter?
Teacher, about the everything included, do you include in the theory for the solving part?
Yeah, yes, of course, theory and problem solving, everything for final exam.
Okay, teacher.
If you are in a rush, maybe it's better to review all the lectures. You should be fine. Because something which are not on the slide I explained in the class. The slide is just a summary, but some of them needs explanation. Mr. Balang.
Yes, sir. Present.
Okay, today, what date is this? February 15. Thiravut.
Yes,ครับ
Napatra.
Yes.
Patong.
Yes.
Rajay.
Yes อาจารย์
Chonikan.
yes ค่ะอาจารย์
Michelle.
Yes.
Michelle, were you present in the last class? I didn't see you.
I have some business to do with my family, so I didn't come last class.
Okay, normally you are always present, that's why I was wondering. Phil is present. Silicon.
Yes, teacher.
We salute.
Yes sir
Yu Chen.
Yes teacher
Sisihang. Sisihang is present or not? Let me see. It's showing offline, no, online. Patompong.
Yeah ครับ
Kongsu. Is Kongsu here? Today Kongsu not present. Martin.
Yes อาจารย์
Kulawik.
Yes อาจารย์
Pichayut.
Present ครับ
Jimma.
Yes sir
Jimma is present. Suanyuan.
Yes
Satawat. Is Satawat present?
Yes, Azan, can you hear me?
Yeah. Yapeng.
Yes teacher
Seni.
Yes, present.
Silipop.
Present
Pitu.
Present
San An.
Yes
Waramet.
Yes
Nabawan.
Present.
Natapop.
Yes, present.
Warapat.
Present.
Nantaya present. Pichayapon present. Mr. Khomchan. Is Khomchan present? I don't see him. Oh no, today not. Piradon.
Yes,
Present. Kitsanapong is present. Atitya
Yes
present. Tasin. Sukaina.
yes teacher
Sirin.
Yes, teacher.
Min Luin U is absent. We'll meet again on next Thursday. The class we can dismiss now.
อาจารย์คะ
Yes.
when will be quiz 2 คะ
I think 2 weeks from now, which is 1st of March, Tuesday. I try to make it Tuesday
Okay.
so that 555 section can attend.
โอเคค่ะ
I'll give
Thank
you the
you,
instruction. Welcome. You may leave now if you have no further questions. 4
Thank you,
minutes left.
teacher.